So the metric system uses prefix multipliers to change the size of units. We need units of different sizes because if I were to measure, say, the distance between my house in Reedley and Fresno City College, and I used the unit inches, I would end up with a ginormous number of inches, and it wouldn't really be all that meaningful to us. And so what unit would I use to measure a distance like that? Kilometers or miles, right? We want a unit that is more on the scale of what we are measuring, so that we would end up with a reasonable number. So, you know, it depends on how you measure it. On the road, or as the crow flies, it's roughly 30 miles, right? So then that's a nice, reasonable number. If we express that in inches, it'd be ridiculous. So in the metric system, instead of having these sort of random relationships between units of different sizes, in the English system for length, there's 12 inches in a foot, 3 foot in a yard, 3 feet in a yard, 5,280 feet in a mile, and I can never remember the yard to mile one. The metric system just uses powers of 10. And you learn one set of prefixes and what they mean, and those apply to all the units. So it really is more economical in terms of what you need to learn. We do use scientific notation a lot in chemistry because we deal with very small numbers, and we also deal with very large numbers. So you should have learned scientific notation before. If you have trouble with it, read Appendix 1A. Where's my pointer? There it is. Appendix 1A in your textbook has a nice review of scientific notation. After looking at that, if you're still kind of swimming around in that, come and ask me, and I'll show you, okay? But I'm not going to take lecture time on that. So the metric system, the SI system, use the same prefix multipliers. It's these guys. Okay, many of these are on the list of things you should memorize, and I believe there are other metric prefixes, but we're not going to care about those. Sometimes you can't do everything you'd like to do, and so you just have to pick and choose what's most important. So these are most important: kilo, centi, milli, micro. Those are probably the most important ones for chemistry. So if you can't get it together to memorize all of the ones on the list, at least do those. Here are their symbols. That's what's used as part of the unit. Notice that as we get above kilo, these are all capital letters. The capital letter ones all make the unit larger. So mega means 1 million or 10 to the 6th. So when we put mega in front of the unit, it makes it 1,000,000 times larger. Kilo's a little weird because it does make the unit larger, but it's a lowercase k. I'm not sure exactly why that is, but most of them that are lowercase letters make the unit smaller. There's 3 M's in here, and so you have to be very careful with those. Capital M is mega, lowercase m is milli. They're not the same. So when you write millimeter or megameter, you need to be very clear that you've got a capital or a lowercase m. And then this is also an M. It's the Greek letter M, mu. It kind of looks like a backwards Y, right, with the tail in the front. But it does need a tail. It's not a U. So this makes a really cool visual pattern, but memorizing the multipliers as these decimal notation numbers is pretty tricky and not very useful. So what you should memorize are the powers of 10. Most of the exponents are multiples of 3. If that helps, this is 3, 6, 9, 12, 15, 18. And going down from milli, minus 3, minus 6, minus 9. It's just these couple in the middle that are different. So if you're guessing, right, because sometimes, like, I don't remember what tera means. So I have to guess because, you know, if you don't answer, you're 100% sure to get it wrong. If you guess, there's a chance that you might get it right. If you're going to guess an exponent that's a multiple of 3. So the multipliers change the value of the unit. just like the exponent does in scientific notation. So if we look at the kilometer, the prefix kilo means 1,000 or 10 to the third. So 1 kilometer is 1,000 meters. Kilo means 1,000 or 10 to the third meters. So let's do a different one. What about 1 megagram? Well, mega means 10 to the 6th. So that's 1 times 10 to the 6th grams. So the M means 10 to the 6th, capital M. So capital M is like a nickname for 10 to the 6th power. I prefer to write it with a 1 times in front of it. When you multiply something by 1, you don't change its value. You could just write 10 to the 6th grams. 1 times 10 to the 6th grams, now that's in scientific notation, and then it's clear how to put that into your calculator. Whereas if you just have 10 to the 6th, you might stumble around there a little bit. Any questions? We'll do more examples.
Do you want it in scientific notation every time?
That's a good question that comes up. Okay, when should I write numbers in scientific notation? When can I leave them in decimal form? Different instructors have different requests. And so it's always a good idea to find out what your instructor wants and give it to them, right? Because a happy instructor is more likely to be lenient when they're grading your papers. It shouldn't be that way, but, you know, kind of it is sometimes. My kind of rule of thumb is if there's more than 3 zeros in the front or at the end, scientific notation is probably a good idea. Because it's hard to just look at like 7 zeros and see that there are 7 zeros. Some people can probably do that. I can't. I have to get my finger out and count the zeros. And that makes me feel like a kindergartner or something. I don't like that. It's also easy then to get the wrong number of zeros when you copy that number or put it into your calculator. And so I take sort of a practical approach. When should we use scientific notation? When it's clearer than decimal notation. Now, if it says to record your answer in scientific notation, then you better use it. If it says express your answer in decimal form, you better do that. But in my opinion, scientific notation is never wrong unless it specifically requests otherwise. Does that answer your question? Okay, so how long is 4.5 megameters expressed in meters? Now this, we're not really doing a big calculation or anything. We're just substituting what mega means into the symbol. So 4.5 megameters. Okay, instead of mega, I want to write what it means. And mega stands for 10 to the 6th. So I'm going to write 10 to the 6th in here. It needs to be multiplied. 4.5 times 10 to the 6th meters. And there's some questions on the worksheet today that are going to ask you to do stuff like this. And sometimes students get it wrong because they don't understand. It's actually something very simple we're asking you to do because it helps us to understand what is this meaning. This is capital M is shorter to write than times 10 to the 6th. Right? So 4.5 megameters is 4.5 times 10 to the 6th meters. Okay, so a volume 7.13 times 10 to the minus 9th liters, how many nanoliters would that be? Well, what prefix has the meaning 10 to the minus 9? Nano. So this equals nano. So that would be 7.13 nanoliters. It's just an abbreviation for 10 to the minus 9. Any questions? Once you get the metric system, it is so simple and beautiful. But you need to persist until it clicks for you. So we talked about units of length, temperature, time, and mass. There are also derived units. So a derived unit is a combination of other units. Units for rates of speed are examples of derived units. If I ask you, well, how fast did you drive on the freeway this morning? You would answer in miles per hour. That's a derived unit because it's the unit miles divided by the unit hours, or you could express it in metric by saying meters per second. So volume is a measure of three-dimensional space, and we can measure that, say, for a cube using a geometry equation. So if we have a cube here, the volume of that cube equals the length times the width times the height. Probably at least remember hearing about that, I hope. Well, if each of these sides is measured in centimeters, oh, here's my other side, then I'm going to end up with centimeters times centimeters times centimeters, right? And that's going to be centimeters cubed. So we can make a volume unit out of a length unit that's cubed. Does that make sense? So meters cubed, millimeters cubed, centimeters cubed, any length unit cubed is a volume unit. But it's derived because it's from a length measurement. Other common volume units are liters, abbreviation capital L, and the milliliter. Let's look at milliliter. 1 milliliter. What does milli stand for? 10 to the negative 3. So that's 1 times 10 to the negative 3 liters. When the exponent is negative, we could also express that as 1 over 1 times 10 to the third liters, or 1/1000th of a liter. It makes the unit smaller. Any questions? So here we have a large cube, and it's 10 centimeters on each side. And the question here is, how many small cubes measuring 1 centimeter would be needed to construct this big cube that's 10 centimeters on a side? 1,000, yeah. Because on each side, you're going to have 10 cubes, because they're each 1 centimeter. And going up, you're going to have 10 cubes, and going back, you're going to have 10 cubes. And so we're going to get 10 times 10 times 10, 1,000. So there are relationships between the different units. Within the metric system, we don't really need a table like this, because we have the table of metric prefixes, and that pretty much takes care of everything. The one exception to that is this guy right here, and he's bigger than all the other things on here for a reason. This is a very simple relationship that is often overlooked, and if you forget that one, you can get stuck in your unit conversions. A centimeter cubed is exactly the same size as a milliliter. And in medicine, they call this a cc. cc stands for cubic centimeter. So the other things in this table mostly relate a metric unit, here the metric unit of length, kilometer, to an English unit of length. So this column is all about length conversions, this is mass conversions, and these are volume conversions. There's only one of these that you need to memorize. And I ask you to memorize it only because we end up using it so much, and that's this guy right here. So these two are ones that you should memorize. An inch is 2.54 centimeters. We'll be talking about significant figures in a few minutes. This conversion is exact. The rest of them are not. So this table is in your textbook. If you need this information on an exam, it will be provided for you either as a separate table or the conversion factor may be given in the problem. But I do not expect you to remember how many grams are in a pound. I don't. I could guess, but I don't remember the exact numbers. So if I can't remember it, I don't expect you to remember it. Density is another derived unit. The ratio of the mass of a substance to its volume. So we can say that density equals mass over volume, or D equals M over V. And this is an equation that you need to memorize as well. And you've probably, hopefully have seen that before. Common units for liquids and solids are going to be grams per milliliter and grams per cubic centimeter. We typically use milliliters for liquid volumes and cubic centimeters for solid volumes, but we understand that they mean the same thing. So density is a physical property. You can measure the density of something without changing what it is. It does depend on temperature. So if the density changes with temperature, that means that either the mass or the volume is changing with temperature. Which one do you think it is? The volume. Because the mass is the amount of substance, and that can't change based on the temperature, but volume can. You may be aware that many substances expand slightly when they're heated. That's why if you've got a lid stuck on a jar, you run it under hot water. It makes the metal lid expand a little bit, and then you can get it off. So it's not a big deal most of the time. But you notice in this table of some common densities, they say at 20 degrees Celsius. They'll always specify a temperature. Do you need to use the temperature in a calculation? Absolutely not. And for most purposes, if you're just close to that temperature, you're going to be fine. It would be different if you were, say, working at 100 degrees Celsius, very different temperature, and doing precise work. Then you might want to look it up. They have tables in a big old fat book, that one up there in the shelf, of densities at some different temperatures. So here we've got charcoal, ethanol, ice, water, sugar, salt, glass, and then some of the metals. And these are listed in order of increasing density. There is only one of these densities that I want you to remember, and that's the density of water. So you should know that one. The density of water is 1 gram per milliliter. Technically, that's at 4 degrees Celsius. It's only very, very slightly different at 20. So that's water's maximum density. If we look at ice, that's just solid water. But ice is less dense than liquid water, and that's why ice cubes float instead of sinking to the bottom. And we see down here things like gold and platinum are extremely dense, 19 and 21 grams per cubic centimeter. It always, makes me laugh. It's like cartoons, it's like they're out to destroy the laws of physics or something. They're just violating everything. And maybe it's just kind of a fantasy that we have as humans, that we could just walk off a cliff and not fall down until we notice that we're off the cliff. But also sometimes in movies, you'll see, the robbers get this sack of gold, right? And they throw it over their shoulder and they run away. You can't do that with a sack of gold. A sack of gold is incredibly heavy. A brick-sized piece of gold, you're going to have a hard time lifting because it's like 20 times denser than water. And water's heavy, isn't it? Carry a big old pot of water or a cooler, it's heavy. Gold's 20 times heavier for its volume. So it's really a bit ridiculous. That brings us to intensive versus extensive properties. So an intensive property does not depend on how much substance you're looking at. You could think of this as an intrinsic property. It's something that's innate to that substance. It doesn't matter if you have a little bit of it or a truckload full. And we can use intensive properties to help us identify substances. Examples of these sorts of properties include density, melting point, and color. So if you think about a copper penny as a specific color, right? If you take a pair of strong tin snips and cut the penny in half, does the color of the penny change? No. The color of it does not depend on how much there is. So ice melts at 0 degrees Celsius. One ice cube will melt at that temperature. A glacier will melt at that temperature. The melting point doesn't depend on how much there is. It's an intensive property. Density is also an intensive property. So density is the ratio of mass to volume. So if you were to measure the density of the penny, right? You've got its mass and you've got its volume. Now you cut the penny in half, and you're looking at 1/2 of the penny. Its mass is half as large, but its volume is also half as large, and so the density is the same. So a small piece of gold, a large piece of gold, they have the same density. Their mass and volume are different. Mass and volume are not intensive properties. Those are extensive properties. They do depend on how much substance there is. So the mass of something, its length, its volume, that will change. So intensive properties can be useful in identifying substances. Any questions? Okay, here's our first real word problem. This one's got a lot of words. Some of these, I think the author is actually writing just to be interesting. And we need to learn how to solve these word problems. When I was growing up, they called them story problems, which made them sound a little friendlier. And this one actually does kind of have a story. So the first thing we need to do is read the whole question. A man receives a platinum ring from his fiancée. Aww. Before the wedding, he notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? Okay, so we go through that, we read the whole question, and then let's pull the numbers out and write them down and see what they are. So we've got 3.15 grams, and we have 0.233 cubic centimeters. So the question tells us that it has a mass of 3.15 grams. So that's its mass. We could also recognize that as a mass by the unit. Gram always measures mass. And then we have this, it says it displaces this much water. What does water have to do with whether the ring is platinum? The volume, yeah. So it's hard. You can't just use length times width times height on something like a ring. It may have curved surfaces, and it's hard. So for an irregularly shaped or a funny shaped object, one way you can determine its volume is by seeing how much water it displaces. So you take maybe a graduated cylinder and you put some water in it and you make a note of the level in the graduated cylinder. Then you drop the ring in and the level of the water will go up because the ring displaces, it pushes the water out of the way. So the water rises in the graduated cylinder, you make a note of what it rose to. The difference is equal to the mass of the ring, not the mass, the volume of the ring. Same thing happens with you in the bathtub. Like, you could try this at home. Bathing is a good thing. So fill the bathtub and try to get it exactly half full. And then get in and notice what happened to the water level. It's going to go up significantly. That difference is equal to the volume of your body that is under the water. So one way they can find the volume of a human body is with a big tank. And you jump into the tank and then the water level rises and they can measure your volume that way. Don't do it with a full bathtub though. It'll go all over the floor. So this is the volume of the ring, right? And sometimes with these questions, it's not going to be just immediately obvious to you. So you may have to think about it. You may have to poke around, ask some questions. Okay, so now we've got a mass and a volume. What can we do with that? Find the density. And here's this big clue up here. Calculating density. Maybe we should calculate the density. Okay, let's try that. So density equals mass divided by volume. It's important to show your work for many, many reasons. So showing your work would be writing down the equation you're using if you're using an equation. Then write it down with the values put in. So 3.15. Always include the units, grams, 0.233 cubic centimeters. And it is super easy. Even if you don't have any learning issues, it is super easy to transpose digits and mess that up. So take a look at it and make sure you copied it down correctly. Always, always include the units. So now get your calculator out. You should always bring your calculator. So 3.15 divided by 0.233. So the density is 13.5, and none of those units cancel out or anything, so they're just going to sit there, grams per cubic centimeter. Okay? Is this ring made of platinum? No. How do we know? We look at the density of platinum. If the ring is pure platinum, it should have the same density, because no matter what shape or size it is, it'll have the same density. So let's go back to that table. Down here. It no longer lets me point all the way at the bottom. It's super annoying. Maybe I can draw down there. The density of platinum is 21. It's not platinum. If we were just comparing densities, what might we think it was? Mercury. Could the ring be made out of mercury? No. Mercury is a liquid at room temperature. It's like making a ring out of water. It's not going to work, right? So how could it have the density of mercury and not be mercury? Could be a mixture, right? If it was, it might have some platinum in it. It might be platinum mixed with a much lighter metal like aluminum. And it may appear the same visually. But when you pick it up, you're like, wait, that's not heavy enough. You can tell the difference between something that's made out of plastic and something that's made out of metal, right? Because the plastic it's lighter for its size. Oh, I lost my thing. Oh, well. But we finished the problem. Is it made out of platinum? No. No, it's not. So next question. The woman in this example is shocked that the ring is fake and returns it. She was not trying to cheat her fiancé. She buys a new ring that has a mass of 4.53 grams and a volume of 0.212 cubic centimeters. Is the new ring platinum? So now we know what to do, right? We've got to calculate the density for this. Density equals mass divided by volume. I'm going to put the mass in 4.53. Somebody's ahead of me and said yes, and you are correct. And I believe that comes out to 21.4 grams per cubic centimeter. Yes, this one is platinum. Any questions?